it's an exponential function, so you repeat the exponential function, and then you differentiate this part, the minus x squared plus y squared, with respect to x, which we'll do in a bit, plus this times the derivative of this with respect to x. So that's just what the product rule gives you. So we're almost there. So we have cosine 4y, sine 3x, exponential, and then here, y squared, that's a constant. The derivative of a constant is 0, so this does not contribute anything. You only have this, so you're going to get a minus 2x in there, and then everything else. So derivative with respect to x of sine 3x, that's 3 cosine 3x. All right, so you have to remember your differentiation rules again. Now the added burden of making sure you're differentiating with respect to the proper variable, and not losing track of that, and keeping everything else constant, d dy. It's similar because we have this part, sine 3x, that does not depend on y. Treat it as a constant, now you pull out. So now you're going to have cosine 4y, then you're differentiating the exponential part, which is going to lead to a factor of minus 2y here. And then from the rest of a product rule, you're going to have the exponential part, and then you're going to differentiate to cosine 4y, which gives you a minus 4 sine 4y. And that's df dy. It works out pretty similarly in this case anyway. Once you have the partial derivatives completed, then if you want to know what it is at a particular point, then you plug in these values. Just wait till the end. And the reason why it's particularly important to wait until the end is because we also have second partial derivatives. All of these, partial with respect to x, partial with respect to y, those are first partial derivatives. They play a similar role as first derivatives in the single variable world. So now we can take these derivatives and differentiate them to get second partial derivatives. So for example, xy is natural log of x plus y squared. So what we can do is compute its partial derivative with respect to x, and I'm going to use the other notation, f sub x. So that's going to give us 1 over x plus y squared. And then you're going to differentiate what's inside with respect to x. What is that going to give you? It's just 1. You get a 1 from here and nothing from here. Treat it like a constant. Then fy, 1 over this, times the derivative of what's inside with respect to y is 2y. Now we can take these and compute second partial derivatives. So now, very good. There are 2 first partial derivatives. There are going to be 4 second partial derivatives all told. You can also do third derivatives. That would, so you'd have 8 of those. We're not going to do that now. No, I didn't ask for it on the practice problems either. So fxx, so it's similar in spirit to a second derivative from a single variable world, so you could interpret it in a similar fashion in terms of concavity and such. What we'll do is we'll take this derivative with respect to x that we got earlier and differentiate that with respect to x again. So how would this go? Squared, you think of this as x plus y squared to the minus 1, and so now it's raised to minus 2, with a minus being put out here. And now you got to take what's inside here and differentiate it with respect to x, which gives you 1. So we get minus 1 over x plus y squared squared. So you just keep the process going. And differentiation naturally is going to work in exactly the same way. You just got to be more careful than you needed to before. But you can do fxy. So that is, so you take the derivative with respect to x that you computed earlier, and now you differentiate that with respect to y. So we have 1 over x plus y squared. So if we differentiate this with respect to y, it'll start out the same way as when we did fxx, but it's not going to conclude the same way. So we'll have minus 1 over x plus y squared times 2y now, because now what's inside gets differentiated with respect to y. Let's take a look at the next one, fyx. So we take df dy, partial with respect to y, differentiate that with respect to x. So let's recall what that is. That's 2y over x plus y squared. Okay, so now when we differentiate this with respect to y, well, we could use a quotient rule. So we have x plus y squared times the derivative of this with respect to y, which is 2, minus this times the derivative of this with respect to y, which is going to be 2y. All right, so now that I have track of my variables again, y squared. And now, well, it's kind of like before, plus y squared squared. And then you take what's inside here and differentiate it with respect to x. That only gives you 1. So we get minus 2y over x plus y squared squared. So here we have minus 2y over x plus y squared squared. Here we have minus 2y over x plus y squared squared. fxy is equal to fyx. So The order in which you apply the differentiation operators with respect to x, y, whatever variables you have, does not change the result. And this is true in general. This is called Merrill's theorem. It requires that these partial derivatives must be continuous, but if they are, then they turn out to be equal. So even though there are 4 second partial derivatives, fxx, fxy, fyx, fyy, which we didn't compute here, you only have to actually compute 3 of them. Same thing goes with if you have a function of 3 variables. There are 9 second partial derivatives altogether, but you only have to compute 6. So the rest of them, you can use this property to figure out what the remaining 3 are. Implicit differentiation. What if a function is not given as an explicit formula, but it's defined by an equation? What you did before, you had an equation involving x and y, and you would differentiate implicitly to find dy dx. The same thing can be done here. So suppose we have z defined by this equation, x squared z plus y squared z plus z squared is equal to 1. So instead of trying to solve explicitly for z, sometimes you won't be able to do that. What you can do is differentiate this equation implicitly to find the partial of z with respect to x, partial of z with respect to y. So to find partial of z with respect to x, we'll differentiate this with respect to z. X and y are going to be treated as constants. So in this case, we're just going to get x squared. Here, we're differentiating, I was differentiating with respect to z. Differentiating this with respect to x, z is not going to be treated as a constant though, because z is a dependent variable, whereas y, that you'll treat as a constant. So what you're going to do is you have to apply the product rule to this. So you have z times the derivative of x squared with respect to x, so that's 2x, plus x squared partial of z with respect to x. It's just like when you had equation x and y, you want a dy dx. Whenever you were differentiating y, you would put a dy dx in there. Here we'll put a partial z with respect to x here. So that covers this term. This term, the z depends on x, y squared, that part is a constant. So we're just going to have y squared partial z with respect to x plus z squared, so that's going to be 2z partial z with respect to x is equal to 0 because the 1 is just a constant no matter what. So now we have partial z with respect to x multiplying this term, and this term. So now what you can do is solve for partial of z with respect to x. We have x squared plus y squared plus 2z is equal to, move this to the other side, minus 2zx. So we can solve. On the other hand, with respect to y, so we have x squared is a constant, so we just have x squared dz dy, plus, there's the y squared z, all of that depends on y, both factors, you got to apply the product rule, so we have 2yz plus y squared partial of z with respect to y, plus the z squared part, that's 2z partial z with respect to y is equal to 0. So you solve this for zy, you can have a very similar form to what we have here. We have minus 2zy over x squared plus y squared plus 2z. So then if you have a particular point where you want to know partial derivatives, then you can plug in the x, y, and z values. Of course, this particular example, you could solve for z, actually, explicitly, because you can write z is equal to minus x squared plus y squared plus or minus x squared plus y squared minus 4, 1 over 2 quadratic equation in z. Now try differentiating that. Even if you could solve for z, you might be better off leaving it